So thank you for the introduction. I'm Agnes Fritsch. My background is about mechanical, physical, chemistry, and electronics. And this is why I'm very, very much interested by all what is about smart maintenance. I'm now a solution director at Altran in the Worldwide Competence Center dedicated to connected solutions and IoT. The intelligent maintenance is at the intersection of our skills in Altran and our offer, that is dealing with product systems engineering, digital software, and industrial operation. And among all the clients here that we are working with, I have chosen to put the focus on Orano. Orano is a company working on the nuclear field. And what is interesting about the work we are doing together with them is that we are developing this intelligent maintenance system that is dedicated to these arms, mechanical arms that you see on the picture. These arms are partly installed in a critical environment and partly in a normal environment. This is named hot and cold. I will show you. Oops, it's going too fast. And the use case about smart maintenance is interesting because it's not only about collecting data, adapting electronics on these arms, but it's also about dealing with legacy systems. It's also about people because these arms are operated by people. And also it's about collecting as much data as possible to improve the training of the people, getting some intelligent maintenance and predicting failure. So it's quite a very complete and complex use case. So up to now, the client is mostly focusing on corrective and periodic maintenance. And now we want to go for more condition-based maintenance. Unfortunately, I'm not allowed to share with you some economical data about this project, because they don't want to disclose the cost of failure. But when I show you the way this is installed, you will see clearly that the impact is tremendous. So what do they want to do? They have equipments that are installed in areas that are not easily accessible. They want to go for corrective, to move from corrective maintenance that is fail and fix to conditional maintenance. They have a huge fleet of such arms, up to 1,000 machines. And also they would like to add some diagnostics and monitoring to prevent failures, to synchronize the maintenance operations on several arms at the same time, and also to train the people for them to allow the arms to have a longer lifetime. So how do we do that? So first of all, these are the equipments. They are supplied by the company La Calène. And as I was not allowed to show you real pictures of the factory, I have taken these things from La Calène in their leaflets, and I thank them for that in case some people are in the assembly. So an arm is something like that, where you have a part of the arm in the hot zone and a part of the arm in the cold zone. And you have operators, and these arms are telescopic. So this is what you can see here. This is the part of the hot zone, and this is the part of the cold zone. And in between here, you have a wall of typically 80 centimeters width. So if you want to record all what is happening here and here, you have this difficulty to go through this natural obstacle. What did we decide to do? So we had to measure all the movements of the arms in order to generate this data, to make a connection between the movements of the arms in terms of movements and speed, and also strain and stress, and the way people are using it, and extract it from this, get the information later when we will have collected enough data of how to make it so that the life cycle of the arm is as long as possible. So for that, we need to measure several amplitude of movements, the azimuth, the rising, the rotation, plus the telescopic arm, as I showed you before. So to do that, we have put some inertial sensors to measure X and Y. We have put some measurement of the counterweight to with a manual Z and an electronic Z made with infrared sensors, plus recording the button push made by the operator. So we had to put all these sensors for the measurement. And the constraint is that we understood quite fast that putting the sensors on the cold only and avoiding having sensors on the hot zone would oblige us to calculate the real movements of the hot zones. I will tell you some ways we have been trying before succeeding, but it's not straightforward, as you can guess. And finally, we need to create models to define the critical parameters and the critical thresholds. The other important point is that this has been done in collaboration with the client, of course, with Obdo making some electronics and with Altran bringing the connected solutions. So we have done the first trial by equipping the arms with 2.4 gigahertz sensors to measure all the movements plus a gateway. And this was not so successful. So we went for another solution where we have been using LoRa, standard LoRa for alerts, to send alerts to the supervision operators, Wi-Fi for the connectivity, and we have put finally wired sensors only in the cold zone. And this was okay, and also it was complying with the standards and not modifying the arm that is certified. Then we had to interface the commands of the MT200, this is the name of the arm, without compromising the arm security features. We had to add some synchronization with a network time protocol to make sure that we had a real-time information. We had to model the smart cards that we have put in the arms to check the integration facility. So we made a 3D modeling for the integration. Then we made the mock-up, and then finally we made the real equipment. This is all the wire system coming from the arms, and this is a deported measurement. We we had to face a problem of the powering of the sensor system because it had to be the same power system as the arms, and there were some interferences. So we had to isolate this in order to prove that we had no impact on the arm. And finally, we had to get real-time data collection, collecting at least every 100 milliseconds. So here are some results about the measurement of the sequences on different trials of the reported measurement done by the system with relation to the real movements. And we have been showing that we were able to get an exact report of the movements of the arm at plus or minus 100 millimeter. And also for the displacement plus or minus 2 centimeters, which was sufficient for what we had to do. Initially, we needed to start with a simple algorithm based on the Euler angles calculation. So we have put some illustration of what it means, because it is also used in the avionics by using the Tate-Bryan algorithm. We thought we would have to use quaternions measurements for the sensors together with the initial sensors of 2.4 gigahertz, but finally it was not necessary. This algorithm is sufficient. Then what we have to do now is to work with Orano to quantify exactly the critical parameters. We have to collect information to anticipate the failures and let them anticipate the failures and synchronize the maintenance of all as many as possible arms at the same time. And also what is very important, training the collaborators. The collaborators are trained by using some templates figures. So for example, they learn to grab a circle, a square, a light object, a heavy object, and they have to learn to do the best movements to do that. And by registering and recording the way they do and all the strain and stresses on the system, they can compare themselves to the nominal and the best way to do like experts are doing. And this is very important to have a more homogeneous way of handling these arms because the operators have a huge impact on the lifetime of the arms. So for the cost efficiency, I'm not able to disclose so much because it's my client's information, but just you have to imagine that by developing these sensors and this electronic and the collection of the data on a local server, it's roughly, let's say, 2,000 euro for the solution. And if you just compare this with replacing the arms to move from legacy arms to a more sophisticated one, there is no way. In that case, the IoT is much more cost efficient. The average failure cost is huge because we imagine that when you have to stop the hot zone to make a reparation, to repair and fix something, it's quite difficult and it has a huge operational impact. And also you imagine that it's important to mutualize the maintenance operations on several arms when they are linked to the same hot zone. So all this to conclude on the fact that this system is very interesting because it handles operation like with the people, real life, because we had to deal with legacy systems and critical fields because there are hot zones and cold zone. And for this kind of things, the IoT is quite relevant and you have to train the system, train the people, and improve the way people are gathering the data based on algorithms. And this is why it's a very complete overview of the kind of things that can be done with such systems. Thank you.
Thank you very much. I'm looking quickly into the Slido for questions from the audience. I think there's always a bit of delay, so we have to check. I mean, from my side, there would be some questions. The one is you mentioned that you're not allowed to use like wired connection in the hot zone. On the other hand, it's also like a radiation zone. Did you consider radiation hardness or radiation damages or for those sensors, or was that not an issue?
Yes, it was. This is the first idea was to equip the whole system with 2.4 gigahertz sensors, measuring really movements in between them in all parts. And we understood that it was difficult because of the radiations to put this in the hot zones. And this is why we have finally decided to report and record the electronic informations, including pushing buttons and electric signals from the arms, calibrate that, and deduce from this, from the cold zone only, of the real movement that was being done in the hot zone. So it's no more now a direct measurement, it is a deduction of the movements, and it works quite fine, by the way, which is less expensive and less difficult, and it does not reduce the global MTBF of the system.
Mm-hmm. Okay. The other question is looking a bit. There's a question: how do you dealing with the lack of real defect data? But I think this was not geared towards you, or maybe to the more general audience. The other question was: you mentioned that the human operator is very important. Can you say a bit more? Is it also like there's a feedback loop that you adjust the training program, or that you like identify different users when they operate these arms with respect to the damage, or is it an overall damage model that you have to consider what the operator is using?
No, there will be some kind of templates of good practice, and this is something that we are developing now, and the client is mostly in charge of that. They want to compare the signature of the movements done by the beginners when they are trained and compare them with the measurement of experts doing that properly. Because it's difficult at the beginning when you start with such systems to avoid brutal movements or huge movements where it's not necessary. And this is where the recording of the movements on the all arms, comparing one operator to the other, and in particular the beginners with the experts, really makes sense, because it's easier to explain to the people when they see the data than when it's too theoretical.
Okay. But this is kind of still had to be done by hand, right? I mean, these adapters or these trainings have to be
we will
done.
see how, yeah, to start, yes, we will see then if we have to make something automated. But by the way, as now we collect all the information, we have access to statistical data, and we will have to collect more and more data to make sure that the interpretation is really good with regards to lifetime of the arms on the training and on the operation side.
Okay. So I think there is no more questions coming specifically to you. I check quickly. I think it's probably okay if we then directly move to the discussion.